Well, it's a cold and very snowy day here on February 20th of 2019 in Minnesota. Many schools are closed for the day, and you can see I decided to work from home to make this video for you. This is Financial Math for Actuarial Exam 2, video number 173. Recently we've been talking about the subject of immunization and doing sample SOA exam problems, but in this video we're going to look at a problem from Broverman's book, 7th edition, problem 7.2.3. a modified version of it. I would also recommend going to my blog, infinityisreallybig.com. The post from a couple weeks ago, Immunization Part 2, has some calculations that are similar to the kind of calculations we're going to see in this video. And then Immunization Part 5 is a post I haven't made yet. I'll put it up there here shortly after I post this video. Alright, there's a lot of heavy-duty content in this video, as there are in many of these things. I really recommend getting a piece of paper and a calculator and maybe some coffee and being ready to think carefully about what I say and double check calculations. It's definitely a challenge, but I always try to make these things really worth your while too. You can really understand the bigger picture if you understand what I say. So we are in the context where we've got cash flows, asset and liability cash flows, and we've got the present value functions. And what's the main overarching goal? The main overarching goal is to, first of all, match present values and durations of these cash flows. That seems like a good thing to do, to try to be able to cover your liabilities by your assets. And it's also a good idea to try to immunize yourself, which in a nutshell means you're trying to cushion yourself against changes in the interest rate, to still be at a surplus position of the assets with respect to the liabilities. And we need to think about these functions. The asset cash flows are AT, occurring at time 0, 1, 2, 3, etc. up through time n. The liability cash flows are LT, occurring at time 0, 1, 2, 3, etc. up through n. You can see those are occurring at whole number values for t, though I will say here at the beginning that later on in this video we are going to consider essentially the same things with non-whole number values for t. And the ideas are still valid. They can still be made valid in that context. Okay, but these are our present value functions. AT is being discounted back to time 0 by multiplying by 1 plus I to the negative t power. As usual, 1 plus I to the negative 1 power is the same as V, which in this video, as in Broverman's book, we're going to call V sub I to emphasize it depends on I, and we are going to plug in sometimes specific values of I, call them I equals I0 into these expressions. So that'll be important to realize. Okay, so these are things you should have seen plenty of times here if you are to this point in these video series. In the background, because we are matching the present values, we are going to be assuming for this entire video that this equality is true. When I is replaced by I0, we are matching present values, so these two summations that you see here are equal when I equals I0. Okay? Alright, 3 parts of the problem. There's only 2 parts in Broverman. Broverman's are parts A and B, but I'm adding a part C down here. Take it step by step. What's the first thing to do? Part A is what you see here. This is the easiest part of this problem. We want to show that if the first derivatives of these functions at I0 are equal, that condition, that equality, is equivalent. Means the same thing as the equality of these two summations. Okay? So that's the thing we're going to see in part A, and again, that's the easiest part. You might wonder, why is this something you would care about? Well, the equality of these summations, as well as the inequality, for example, of these summations, are things that are, well, for one thing, a little easier to compute by hand than the derivatives. And for another thing, once you know the cash flows and you know the interest rate, these things are easier to calculate on, for example, spreadsheets. Spreadsheets can't calculate derivatives. Mathematica, the program I'm using, can calculate derivatives, but spreadsheets can't do that. So that's, I think, kind of the motivation, is these summations, the equality and the inequality, are things that are more easily computable, including by spreadsheets. Part B, we are showing that, once again, in the condition where present values have been matched, if we also assume the derivatives, the first derivatives are equal, then the following are all equivalent. 3 conditions here. 1, 2, and 3. This first condition, that the second derivative of the asset cash flow present value at I equals I0 is greater than the second derivative of the liability cash flow present value function at I equals I0. That's the main condition we've been thinking about for Redington immunization, right? We've been thinking about the h of I function, which is the difference, this function minus this function, and we have seen that when it's at I equals I0, when it's 0 and its first derivative are 0, when the second derivative is positive, that means the graph is concave up. That means it looks like this and there's a local or relative minimum at I equals I0, which means you are Redington immunized. Not necessarily fully immunized. The graph of h of I might not be positive for all values of I, but certainly near I equals I0 it will be positive. And that's what cushions us against changes in the interest rate. So that's the main condition we've been thinking about recently, but that's equivalent to two other conditions. This inequality right here, and this inequality right here, which is kind of strange. Looking, you might wonder where this is coming from. I'll probably think about that in a future video, where di, as explained in Broverman, represents either Macaulay duration or modified duration. But here's a little secret. It actually could represent other things too. Anything independent of t, this inequality will still be equivalent to this inequality, which seems strange. So why would you focus on putting durations in there when d of I could really be anything that doesn't depend on t? Okay, I think there is a reason for that. We'll again look into that in future videos. Part C is what I've added to modify this problem. From this, what we do in Part B, we want to interpret conditions 1, 2, and 3 here in the context of the last video. I'll put a link to video 172 here up in the upper right corner. What was that context? Actually, that context occurred in video 171 as well. We have two liabilities, 500 paid at time 1 and 1,000 paid at time 4, and two assets, A0 or X paid at time 0, and why is there a 3.57207 there? Well, let me explain that in a second here. Let's just call it Y, occurring at some future time, where in the last video I called that future time little y. Those are the cash flows. The interest rate is 10%. I want to interpret these inequalities in that context. What does that mean? Well, if you look at video 172, near the end of the video, I talk about trying to find a minimal value of y that, well, in a sense, by being a minimal value of y, doesn't quite lead to Redington immunization, but almost does. We saw that in video 171, even though we matched present values and durations, that we were not immunized. The second derivative of the h function was negative. The graph of h of I was concave down. But then I said maybe the second payment can be further in the future at some little y that we need to determine to make that graph become concave up. And the boundary value where the second derivative is 0 is the 3.57207. That's not a whole number value. So that's why I said near the beginning of this video that these summations, even though they are written in terms of t being a whole number, we could think about similar functions when t is not a whole number, and these ideas are still going to carry over. We will see. Okay? All right. Take a deep breath. I need one too. Here we go. Again, part A is not so hard. It's just a matter of calculating the derivatives of these functions, this one and this one, with respect to I. Treat the A's, the L's, and the T's as constant. So you need the power rule. You need to bring down the negative t in both cases and subtract one from that exponent to get a new exponent of negative t minus 1, which is exactly what you see both here and here. And then, if you want, and it is helpful for the purposes of doing part A, go ahead and factor out a 1 plus I to the negative 1, which is v or v sub I, and go ahead and factor out a negative sign in both cases. And that now helps you see the equivalence of this equality with this equality. It's just a two-step thing here. If this is true, then by the formulas we just calculated, these are going to be equal. And then get rid of the negative VI's by canceling. You know, VI is not 0, we can cancel it on both sides and get this quantity right there. Okay. These are equivalencies. They go back the other direction. You notice these arrows are two-directional. If this is true, we can multiply both sides by negative VI and get this to be true. But because of the derivative calculations we did, that means this is true. Okay, so part A is relatively easy. That's good. Now it gets a bit tougher. Let's make this a little smaller here. Now we calculate the second derivatives for part B. What was part B again? Part B was that if this is true, then these three things are equivalent. Okay? So let's go ahead, we need the second derivative, so let's go ahead and calculate the second derivative. We again use the power rule. You could also say we're using the chain rule, but the derivative of 1 plus I is 1, so it doesn't really come into play. So I look at this formula right here and this one right here. I need to bring down the negative t minus 1s in front, here and here. I need to subtract 1 from the exponents to get negative t minus 2, here and here. And then I can factor out a 1 plus I to the negative 2, which is the same as vi to the positive 2, here and here. And then it's a good idea, if I want to ultimately use part A really, and the fact that I'm assuming the first derivatives are equal here so that I can use part A, to use properties of summations. Well, first the distributive property, take this expression and distribute it through the parentheses, and the same with this one. And then break apart the summations into two summations, here, and then here and here. Essentially, that's the commutative property that allows you to reorder things that makes that work. Okay? This last sentence that I have here is not necessary to include, but it is interesting to note. Since we have these derivative facts up here, we can say these two equations are true as well. These summations, with the vi squared in front, one of the vi's can be factored out and a negative sign can be factored out, leaving you with minus vi times the derivative. Okay, not something necessary to do, but if you want, it's part of what you could think about to do the problem, which is actually what I did here in the next section. So again, the background assumption is the derivatives are equal, so those summations that you see here are equal. Notice, for emphasis, I is equal to I0 with these summations here. We are assuming we've got a specific value of I. And again, VI is non-zero, so VI squared is positive. And you get these equivalencies right here. Let me widen this now so it's easier to see. You get these equivalencies. If the second derivative of the asset present value function is greater than the second derivative of the liability present value function at I equals I0, that by these formulas here and here is equivalent to this inequality. And again, since I'm assuming the first derivatives are equal, I can cancel this, and also cancel it with the negative signs there, leaving this thing here being greater than this thing. And then I can cancel the vi squareds from both sides, and the inequality doesn't change direction because vi squared is positive. So that gives me this, and then the logic can reverse. I can multiply both sides by vi squared, and then do the subtraction from both sides because I'm assuming those two things are equal again. That's part of the assumption. Oh, and I'm realizing I have a typo here. Sorry. This should be L's here, here, and here. If you noticed that a minute ago, good for you. Okay? All right. So that gives us the equivalence between 1 and 2. Okay? If I can show also that 2 and 3 are equivalent, then I'll be done, because that'll also mean 1 and 3 are equivalent. Okay, so that's the next goal, is to show 2 and 3 are equivalent, to show, or maybe to show 1 and 3 are equivalent. Let's see here, what am I doing here? The background assumption for this whole problem is, again, that the present values are equal. I haven't used that here in part B yet. Let DI represent Macaulay or modified duration. I'm just going to do a calculation here first. And again, actually, DI could be anything independent of t. It doesn't actually have to be Macaulay duration or modified duration, but pretend it is. Do this calculation. We can expand this. T minus di quantity squared is by FOIL, t squared minus 2t di0 plus di0 squared. And then again, you can break apart the summations like this. And again, that's really the commutative property. And I can do the same thing with the liabilities. And no typos there, it looks like. Okay? All right. So that's just a calculation. So now use what you're assuming. We're assuming the present values are equal. That's the background assumption for the whole problem. And we know these two things are equal because we're assuming these two things are equal. That's really from part A. Okay? So now you can essentially get your equivalencies. This inequality is equivalent to this one right here that goes over two lines, because essentially I'm subtracting and adding equal things from both sides. Okay? And those two things are this and this. So we get the equivalence of these two things. That was the point of this part of part B here. Okay? And again, I never used the fact that d of I0 was either Macaulay or modified duration. It's just a quantity that doesn't depend on t. Okay? It does depend on I0, but it doesn't depend on t. This thing is going to be true. So again, you might wonder, why would we then think about these inequalities when d of I0 is either Macaulay or modified duration? And I think it's computational convenience, you might say. And there might also be some statistical interpretations we'll get into in a future video. All right, we're almost done. Now we're on to part C. We want to check all this in the context of video 172, where again we have these asset and liability cash flows. And again, the second asset cash flow is at time 3.57207. So it doesn't exactly match what we're assuming with the summations that the t's are whole numbers, but it does work still. Okay? And again, we're not actually going to get inequalities here. When we interpret this in the context of 1, 2, and 3, we're actually going to get equalities, because again, this 3.57207 is at the boundary or where the second derivative changes from negative to positive. It's going to be equal to 0 essentially there. If we increased that time of payment a little bit, then we get a positive second derivative for the h function, and Redington immunization would be achieved. The x and y values would change a little bit because of that, but don't worry about that. So we are going to get equalities here essentially for these calculations. So we're having Mathematica do the calculations. You may want to check these things with your calculator here. Here are the present value functions. They're now entered into Mathematica. I can evaluate them both at I equals 0.1. These are the present values of the cash flows, and they are matched up to at least a certain amount of rounding. Yep, to the nearest cent, you might say. 1137.56 are the present values. The durations are matched. Now, the first derivatives themselves are not the durations themselves, but they are the things we've been calculating and setting equal to each other to make sure durations are matched. These are actually a little off to the nearest cent, but that's probably a rounding error. Here are the modified durations right here. Recall modified duration is the second derivative of the negative relative rate of change, which is actually a positive quantity. Take the derivative, divide by the function, put a negative sign in front of it. For both cases, for both the assets and liabilities, we get the same thing. Again, very close. Here are the Macaulay durations. Based on the definition of the Macaulay duration is a weighted average of times of payments, essentially by, where the weights are the present values divided by the entire present value. The 1137.56 here is the entire present value. So these are the Macaulay durations, and they are matched as well. Just a little side note here, modified duration you should remember is Macaulay duration divided by 1 plus I, so take 2.80127 or 2.80126, we should get essentially these two things. I is 0.1, so that's 1 plus I is 1.1, and we do get a match, this one. Now we're on to interpreting 1, 2, and 3. Okay, we're going to see the second derivatives are actually matched when the little y, the time of payment, is 3.57, whatever it was. Sorry, forgot. 3.57207, I'm looking up there from the last video. It's near the end of the last video, by the way. These things are the same, but again, if little y was a little bit bigger, then this second derivative would be bigger than this one. These summations are matched. Again, if little y were a little bit bigger, then we'd get an inequality. So these are the summations that you see here. You notice we've got a 0 squared, that's the first t squared, times a0, and 3.57207 squared times a sub 3.57207 times 1 plus I to the negative t power. And then we have, this is the liability cash flow sum. Liabilities of 500 and 1,000 at times 1 and 4. These things are equal. And then these summations are equal as well. And again, you get an inequality if little y were a bit bigger. This one is the modified duration, and this is the Macaulay duration. In each case, we get equality in both of these. Okay? And then finally, again, di is any quantity independent of t. What did I pick? I picked 10 here in both cases. 10, 10, 10, 10. And there we go. Doesn't matter. I could change it to something else. We get the same thing. Thanks for watching.